Hi everybody. So in today's lecture, I'd like to talk to you about Laplace's equation. But before I introduce that concept, let me do a little bit of review because we've been talking about some pretty heavy stuff over the last couple of lectures. So first, let me remind you about Gauss's law and the differential form of Gauss's law, which we've talked about over the last couple of days. Okay, so the integral form of Gauss's law is shown here in this top equation. And what it says is that the electric flux is defined as the integral over a closed surface of the electric field vector dotted with dA, where A here is an area vector and the direction of A is pointed perpendicular to the surface and outwards, okay? And this is equal to the total charge enclosed by that surface divided by the permittivity of free space, epsilon naught. Now, I've got here two expressions. You can either do a discretized sum, so if you have a bunch of point charges that your surface is enclosing, then you can just sum up and find the total charge of all the point charges and divide that by epsilon naught. But if you have a continuous charge distribution, right, then in order to find the total charge enclosed by that surface, you might have to integrate that charge density, shown here as rho, over the volume. And that will give you your total enclosed charge, and then you divide that by epsilon naught. Okay? So that's the integral expression of Gauss's law. Now, of course, in words, Gauss's law says that if you have a net flux, a net electric field into or out of the surface, then that's caused by a charge that must be inside that surface. Okay? All right, now in our differential form of Gauss's law, we utilize some concepts and definitions from vector calculus. And from vector calculus, we know that if you have a vector field, any vector field will do, but here we're focusing on the electric field, okay? So if you have a vector field, then the integral over a closed surface for that vector field, here shown as E dot dA, right, is also equal to the integral over the volume of the gradient operator dotted with that vector field, okay? So, since we have here the triple integral 1 over epsilon naught triple integral of rho dV equals to this area integral over the closed surface of E dot dA, and since E dot dA is equal to the gradient operator dotted with E integrated over that closed surface, then that means that we can set this triple integral of del dot E over the volume equal to the triple integral of rho over epsilon naught over the volume, okay? And that gives rise to this differential form of Gauss's law. Del dot E is equal to rho over epsilon naught, okay? So that's our differential form. So, in words, Gauss's law says that if you have a net flux of electric field into or out of a surface, that net flux has to be caused by a charge enclosed by that surface. In words, the differential form of Gauss's law says that if you have a charge density, rho, then that will cause the electric field to diverge, okay? In other words, it'll cause it to split off and spread out, or converge in, right? So there'll be some change of the path of the electric field, a divergence in the field if you have a charge density. Okay, so that's the differential form of Gauss's law. Okay, so I think I said all that in words, right? Gauss's law says that in order to have a net field flux into or out of a closed surface, you have to have a source of charge inside that surface, and that source of charge causes the field to diverge. Okay, now we also had the relationship, and this is also a review from a previous lecture, that you can relate the electric field E to the electric potential or voltage symbolized in our textbook by phi, right? You can relate those two via the gradient operator shown here as del, okay? Now, E is equal to the minus gradient of phi, okay, minus grad phi. And if you take that and plug it into Gauss's law's differential form, del dot E equals rho over epsilon naught, then what you get is, plugging in for E, del dot minus grad phi equals minus del squared phi, okay? and that equals rho over epsilon naught. So that's taking Gauss's law, basically, and subbing in for the potential. Now, that equation is known as Poisson's equation, minus grad squared phi equals rho over epsilon naught. That's Poisson's equation. And it relates the potential phi directly to your charge distribution rho. Okay? Now remember that in Cartesian coordinates, the Laplacian is given by del squared is equal to the partial with respect to x squared plus the partial with respect to y squared plus the partial with respect to z squared. So the second order derivatives there for those Cartesian coordinates. Now that one you might want to memorize, okay, but I don't expect you to memorize the Laplacian and other coordinate systems, and they're actually given on the inside back cover of your textbook. So in cylindrical and in spherical coordinates, cylindrical is top here, del squared, and this is just as applied to any random function, which is called f here. But del squared f is equal to 1 over r, partial with respect to r times partial fr, plus 1 over r squared, partial squared f with respect to theta squared, plus partial squared f with respect to z squared. So that's cylindrical coordinates, okay? And then spherical coordinates is down here at the bottom. And we'll do an example with spherical coordinates in just a second, okay? So just remember that it's this Laplacian in Cartesian coordinates is pretty straightforward, but you can't don't make the mistake of thinking that your Laplacian in spherical coordinates is just, you know, partial squared with respect to r squared plus partial squared with respect to theta squared. It doesn't work that way, okay? And there's a more complex expression, and it's down here, all right? Okay, so that was some of the ideas and materials that were covered in the last couple of lectures. Okay, we introduced Poisson's equation, and we introduced the differential form of Gauss's law. And also, I reminded you of something from vector calculus, which is this Laplacian and then the gradient operator. Okay, so the Laplacian is the del squared, the gradient operator is just del. Okay. Now, what we've done is basically now we have a system. If you have any one of those three quantities, the electric field, the potential, or the charge distribution, if you have any one of those things, then you can get the other two via the relationships that we've covered to this point, okay? In other words, if you have the charge density rho here, then you can get the electric field from that by integrating directly over that charge distribution to find the electric field at a point, as is shown here. Okay, so you can do that. And if you have the charge density, right, then you can obtain the potential by integrating directly over a point. Okay, now they're also related via these differential relationships. So if you have the potential, you can take two derivatives. You can find your del squared operator, apply it to your potential, and multiply it times some constants, and that'll give you your charge distribution. Okay, so you can find any of the other two variables from one of the variables. All right, so that's nice. Now, the new material for today is Laplace's equation. Okay, so the Laplacian is the gradient operator squared, del squared, right, or del dot del. And so Laplace's equation is a special case of Poisson's equation in which the charge distribution is zero. So in other words, it's the solutions for empty space. All right, so if there is no charge, then rho is equal to 0, and that means that minus del squared phi is 0, right? And you end up with the equation del squared phi is equal to 0. Now, if you have functions that satisfy Laplace's equations, then those are called harmonic functions, okay? And so they're solutions for empty space where the charge distribution is equal to 0. So I want to do an example problem here, okay? Let's say that you have a point charge, right, plus Q, and it's establishing an electric field all around it. But you're not looking at the point charge itself, you're looking at some empty space near a point charge, okay? Now, the empty space near that point charge, you could find the potential function just using our expression for point charges. So that expression is that the potential, the electric potential, is equal to kq over r, where k is the Coulomb constant, which is 1 over 4 pi epsilon naught, and it's equal to 8.99 times 10 to the 9th in SI units, okay? So there's your expression for the potential when you are away from the point charge by some distance r, and we're going to assume that the space there is empty all around it of charges, okay? So this point charge is all you have to worry about. Okay, now, this potential expression has no explicit dependence on theta and phi, okay? And so, remember, we're in spherical coordinates here. This is the del squared operator we're dealing with, but this second term and this third term here, they require explicit dependence on the angular quantities theta and phi. And kq over r doesn't have any explicit theta or phi dependence, okay? So, that means we just have to worry about that first term in our Laplacian. Okay, so the first term in the Laplacian is 1 over r squared partial with respect to r of r squared times partial phi with respect to r, okay? So, let's go ahead and find out this value. If you take the partial of kq over r with respect to r, which you would have to do in this term, you end up with minus kq over r squared, right? Because the k and q are constants, you pull those out front, and then you're just taking the derivative of r to the minus 1, which gives you minus r to the minus 2, okay? So that's what this minus kq over r squared is. Now, the next bit, you multiply that partial phi with respect to r by your r squared, okay? And so if I multiply r squared times minus kq over r squared, my r squareds cancel, okay? And then I'm just left with minus kq there on the inside. Now, I had to take the partial with respect to r of minus kq. But k and q are constants, okay? And so that gives me 0, all right? So this potential satisfies Laplace's equation, which is that del squared phi is equal to 0. Now, that's just one example, okay? That's just one example. There are a bunch of examples of solutions to Laplace's equation. So there's a bunch of examples of harmonic functions. And you can Google that if you want to and see how many examples you can come up with, all right? Now, there's some interesting fallout from Laplace's equation, which is del squared phi is equal to 0. Remember that these solutions to del squared phi equaling 0, the solutions to Laplace's equations are called harmonic functions. And those harmonic functions, they have some really interesting properties. So we're going to discuss a couple of theorems that apply here. Here's the first one. The theorem goes like this, and this is quoting from your textbook, Purcell and Morin. If an electric potential function phi satisfies Laplace's equation, then the average value of phi over the surface of any sphere, not necessarily a small sphere, right, but any sphere, is equal to the value of phi at the center of the sphere. Okay? All right. So if an electric potential function phi satisfies Laplace's equation, then the average value of phi over the surface of that sphere is equal to the value of phi at the center of the sphere. All right. So let's go back to our example of kq over r for a point charge. Now, what I've done to show that this theorem is true is I've written a little VPython program. But let me outline what that VPython program does before I run it and show it to you, okay? So basically, here's my little point charge q, right? And I am looking at a sphere that is in empty space next to my point charge. Now, it could be any sphere, all right? Any sphere, this will work on any sphere. I'm just going to do one, though, to show you what I mean. So I say that my point charge here is a 1 nanocoulomb charge, all right? And that the sphere that I'm going to look at is centered 1 meter away from this point charge. And I can call this line that connects the center of my sphere to Q my x-axis, just for simplicity's sake, okay? Now, I am 1 meter away from that point charge, and I'm going to look at a sphere that has a radius of 1/4 of a meter, okay? And then what I'm going to do is, I'm not going to find it at all points over the entire sphere, all right, just to make my program a little easier to code. I'm just going to look at a circle. But I think what this circle demonstration will do is show you that this is a generally true thing, okay? So I'm going to find the electric potential at points on this circle, like these ones shown by the X's here, all right? And then I'm going to find the average of those potentials or voltages that I've got. And then once I find that average, I'm going to compare it to the value of the potential at the center of that circle and show you that those values are the same. Okay? Now, here's the link to the code that I've got if you want to play with it yourself. But I'm also going to pull it up here and show it to you. Okay, so here's my code. Just to run through it really quick, I'm going to talk about how to calculate potentials in a separate lecture. But in this one, basically, first of all, I'm just creating my source charge. I'm making it red, and I assign an attribute that is its charge of 1 nanocoulomb, right? And then I'm creating an empty list, which will be the potentials of the on the points over the circle. And then I'm going to set up a while loop, okay, and look at a bunch of different points on that circle, right? Using my while loop. So I'm taking steps in angle of pi over 12. You can take whatever you want, right? Here's my radius of 1/4 meter. And then I'm going to create a running sum of the potentials there for my circle, okay? Here's my while loop. I'm going to run my while loop. I'm going to walk all the way around my circle from 0 to 2 pi in steps of pi over 12, right? And then here's my observation points. My observation points are going to be little blue circles so that you can see what I'm talking about and where I'm observing. Then for each one of those observation points, calculate my voltage, right, or my electric potential at each one of those observation points. And then I add that potential to my list, which I created, and I also add that potential to my running sum so that I can find my average. And then I exit my while loop once I get theta to 2 pi. Okay? Then I calculate my average. So every step along the way, I've had a running sum of my potentials that I have in each step of the while loop. By the time the while loop exits, I've got all of my potentials. To calculate my average, I just divide that running sum by the length of my potentials list. So however many items I have in the list. And then I print out all my potentials. I tell it to print what the average of the potential is. I calculate the potential at the center of my sphere, and then I tell it to print out what that value of the potential at the center of the sphere is. Okay? So let me run this code. Here's my source charge. It's in red. Here's my observation points. They're in blue. Okay? So I'm looking here at the potentials at every single one of those observation points. Here's the values of my potential at every single one of those observation points. Okay? The average of the potential for all of those observation points is 9 volts. And the value at the center of the potential is also 9 volts. Okay? Now you might say, hey, that's not quite the same. Okay, but that's just because, you know, I've got a finite number of points. If I were to really do the thing over the entire circle, then it would be better. So you can see here that if I make my angle steps smaller, right, and then have more points, then it's going to get, these values should get closer and closer. Okay? So that's the code I've written. And you feel free to play with that code on your own too. Okay? So I think that shows that this theorem is true, that if you look at the potentials over, the average of the potentials over the surface of any sphere, in a region that satisfies this Laplace equation, that it'll equal to the value at the center. Okay? Okay, so that's one theorem. The other one that I want to talk about today is Earnshaw's theorem. All right? So here's another example of a great property of harmonic functions. Using the ideas from Laplace's equation, you can show that it's impossible to construct an electrostatic field that will hold a charged particle in stable equilibrium in empty space. Okay? So, you're never going to be able to construct an electrostatic field, static field, that will hold a charged particle in stable equilibrium in empty space. So there's a lot of points there to break down. So let's think about all the possible counter-arguments that someone might have for this Earnshaw's theorem. So first of all, you're thinking, wait a second, that's not right. I can have a construction of charges and then make an empty space point that would be equilibrium for a charge. So for example, let's say that these three red circles, which are equally spaced here, are equal magnitude point charges, okay? Let's say that I fix in space this one on the left and this one on the right. So they're being held in place, right? I don't know, maybe it's on the end of a stick or something, I don't know. And then you take this charge here and put it dead in the middle of those two charges that are held fixed in space. If that's the case, this thing won't move, right? Because there'll be no net force on it. It'll be repelled from the force on its from the charge on its left, and it'll be repelled equally from the charge on the right. And so you'll have these forces in opposition, and it'll be in equilibrium. Okay, that's true, but it's also not a stable equilibrium. Remember, Earnshaw's theorem demanded a stable equilibrium. A stable equilibrium requires that if I give it a little push, that it stays steady and it doesn't move. But look, if I give this charge a little push, it'll fly off and never come back, right? I mean, so this is not a stable equilibrium, okay? Now, you might be thinking, okay, but what about something like this, where I have electric field lines, as shown here in these orange arrows, that are all pointing inward, right? And in those situations, yeah, I could have a charge that I would put, say, right here in the center, and that charge would be in a stable equilibrium because it would feel a force from all sides, and if I gave a little push, it would just go right back. And you're right, that would be a stable equilibrium, but it would also not be an empty space, okay? So how do I know that? Okay, well, let's apply Gauss's law. If I apply Gauss's law here, and here my enclosed surface, right, is going to be this dashed line, then you can see that there is a net flux here, okay? And if there is a net flux, then there must be some charge enclosed by that surface. So that means that this isn't really empty, okay? Because I'm going to have something inside here, and I'm just not showing it in the picture, okay? So that's not empty space. I hope that makes sense. So, for example, you could have a stable equilibrium with a positive charge if you had it inside of a negative uniform charge density. So if I had a negative uniform blob of charge and I stuck a positive charge in the middle of it, it would stay right there. It would be super happy, right? But that's also got stuff there, and that means that the space is not empty, okay? Earnshaw's theorem requires empty space. Now, here's one other thing. Earnshaw's theorem also requires that it be an electrostatic field, okay? So you can hold a charge stationary if you have an electric field that oscillates in time. So you can have an electric field that's wiggling, right? Like maybe a photon or something has an electric field that oscillates up and down. And in that case, you can have the particle in equilibrium, and it would be pretty stable. But it's also not static, okay? So there you go. So I think the important thing to remember about Earnshaw's theorem is all of the, little finer points here and the carefulness of this wording. An electrostatic field that will hold a charged particle in stable equilibrium in empty space. Okay, so that's why I emphasize those words. All right, I hope you understood all that, and I'll see you next time in class.